The five-number summary is one of the simplest and most useful ways to describe a numerical data set without getting lost in every single data point. Instead of listing all the observations, we reduce the entire data set down to 5 key values that capture location, spread, and extremes. Those 5 values are the minimum, the first quartile Q1, the median Q2, the third quartile Q3, and the maximum. Think of it as a snapshot of the distribution. The minimum and maximum tell us how far the data extend overall, and the quartiles and median tell us how the data behave through the middle. If you know these 5 values, you can say something meaningful about where the data are centered, how variable they are, and whether the values appear tightly clustered or widely spread. The big advantage here is that we don't have to assume the data are bell-shaped or symmetric. This summary works no matter the shape. Now let's talk about what each of these 5 numbers is really telling us. First, we get information about location, where the data are centered. The median is the key player for location in the 5-number summary. It's the point where half the observations fall below and half fall above. So it describes a typical value in a way that is not easily thrown off by extreme points. Second, we get information about spread, how much the data vary. The most basic spread measure connected to the 5-number summary is the range, which uses the extremes. That's easy to compute and easy to interpret. It's the full width of the data set from smallest to largest. But the range can also be heavily influenced by just one unusually small or unusually large value. So we typically want a second measure of spread that focuses on the middle of the distribution. That's where the quartiles come in. The interquartile range, or IQR, is one of the most important quantities tied to the 5-number summary because it measures the spread of the middle 50% of the data. The definition is straightforward. It is Q3 minus Q1. Here's how to interpret that. Q1 is the point where about 25% of the data lie below it, and Q3 is the point where about 75% of the data lie below it. So the distance from Q1 to Q3 captures the central half of the observations. If the IQR is small, the middle of the distribution is tightly packed, meaning most values are fairly similar. If the IQR is large, the middle of the distribution is more spread out, meaning typical values can differ quite a bit. And one of the biggest reasons the IQR is so useful is that it's resistant to outliers. A few very extreme points can stretch the minimum or maximum, but they usually don't move Q1 and Q3 very much because quartiles depend on the ranking of the data and where the middle observations fall. So the IQR gives us a stable sense of spread, even when the data set has some unusual values. So why do we lean on the 5-number summary so often? The main reason is that it doesn't rely on assumptions about the shape of the distribution. Many summaries, like the mean and standard deviation, are most informative when the distribution is roughly symmetric and not dominated by extreme points. But real data aren't always that nice. Sometimes distributions are skewed, meaning they have a longer tail on one side than the other. Sometimes datasets include outliers that are far away from the rest of the values. In those cases, summaries built from quartiles and medians are typically more reliable. The 5-number summary works well for symmetric data, skewed data, and data containing outliers because it is robust. It gives you the extremes, but it also gives you a middle picture through the quartiles and median. And when we pair the 5-number summary with a visualization, especially a box plot, we get a very quick, informative diagnostic of a distribution. In exploratory data analysis, that's exactly what we want, a tool that gives us a clear sense of what's going on before we jump into modeling or deeper inference. Now we transition from the numerical summary to a visual summary, the box plot. A box plot, sometimes called a box and whisker plot, takes the ideas of the 5-number summary and turns them into a compact graphic. The goal of a box plot is not to show every data point. Instead, it highlights the key features of a distribution, where the center is, how spread out the data are, whether the distribution looks symmetric or skewed, and whether there may be potential outliers. The reason box plots are so popular is that they balance simplicity with usefulness. In one small figure, you can communicate a lot. You can see the middle 50% of the data. You can see the median clearly, and you can see how far typical values extend before we start seeing extreme observations. And later, when we want to compare groups, like test scores from two different classes or incomes across different regions, box plots become even more valuable because you can line them up side by side on the same scale and compare distributions quickly and fairly. Let's break down the structure of a box plot, starting with the box itself. The box spans from the first quartile Q1 to the third quartile Q3. So visually, the bottom edge of the box marks Q1 and the top edge of the box marks Q3. That means the box contains the middle 50% of the data. The length of the box is the interquartile range. Inside the box, there's a line marking the median, Q2. That line tells you where the center of the distribution is in a resistant way. If the median line is near the center of the box, it suggests the middle of the distribution is relatively balanced. If it's closer to one edge of the box, it suggests the data may be skewed. So in just the box itself, we already get a picture of center and middle spread, two of the most important things we want when describing a data set. Next come the whiskers, which extend outward from the box. The whiskers are meant to summarize the range of typical values, values that are not considered unusually far from the rest of the data. Under a common and widely used convention, the whiskers extend to the smallest and largest observations that are within 1.5 times the IQR of the quartiles. The key idea is that we use the IQR as a benchmark for what counts as typical spread in the data set. Now, the whiskers don't necessarily stop exactly at those cutoff values. They extend to the most extreme observed values that still fall within those limits. Any observations beyond the whiskers are plotted individually, often as points, and labeled as potential outliers. This is important. Those points aren't automatically bad data. They're simply values that deserve attention because they are unusually far from the central portion of the distribution. This approach prevents extreme values from stretching the scale so much that we can't see the rest of the distribution clearly, while still making sure we don't hide the extremes. One of the reasons box plots are so widely used is that they are resistant summaries. Because box plots are built from quartiles in the median, they're largely unaffected by a small number of extreme observations. Imagine you have a data set where most values fall between 50 and 80, but there's one value at 200. If you plot all the data as a dot plot or histogram, that extreme value might stretch the axis. And if you summarize with a mean and standard deviation, that extreme value can pull the mean upward and inflate the standard deviation. But a box plot doesn't behave that way. The quartiles and median depend primarily on the order of the data, so unless the outliers are numerous enough to change, where the 25th, 50th, or 75th percentiles fall, the box and median stay relatively stable. This makes box plots especially useful when distributions are skewed, or when you suspect outliers. In practice, many real-world variables like incomes, medical costs, reaction times, or certain sports performance measures are skewed and contain unusual values. In those settings, a box plot often gives a clearer picture of typical behavior than a plot or summary that is overly sensitive to extremes. Box plots can also give us a quick sense of the shape of a distribution, even though they don't show fine detail. One thing we look at is where the median lies within the box. If the median is roughly centered between Q1 and Q3, that suggests that the distribution is fairly balanced in the middle. And another thing we look at is the whisker lengths. If the whiskers extend about the same distance above and below the box, that also points toward a roughly symmetric distribution. On the other hand, if the median is closer to the bottom of the box and the upper half of the box is larger, or if the upper whisker is noticeably longer, that suggests right skewness, meaning the distribution has a longer tail on the high end. Similarly, if the median is closer to the top of the box and the lower whisker is longer, that suggests left skewness. It's important to remember that box plots don't show every bump and cluster the way a histogram might, but they do provide a fast diagnostic: symmetry versus skewness, tight spread versus widespread, and whether there are potential outliers worth investigating. A major strength of box plots is how well they support comparing groups. If you have two or more categories like different classes, different teams, different treatments, or different populations, you can put multiple box plots side by side on the same scale. Then you can quickly compare centers by looking at the medians. You can compare variability by looking at the IQRs, meaning the box lengths. You can compare skewness by looking at where the medians sit within the boxes and how the whiskers differ. And you can compare outliers by looking for individual points beyond the whiskers. This is one of the reasons box plots are staples in exploratory data analysis. They're compact, they're interpretable, and they allow comparisons that would be harder to make if you were only looking at raw numbers, especially when group sizes are moderate or large. Side-by-side box plots let you see patterns and differences at a glance and help you decide what to investigate further. Now let's work through an example to make all of this concrete. In example 1, we have two groups of exam scores. Even before doing any formal computations, we can already anticipate some differences. Group A values are all clustered in the 70s, so we expect relatively low variability. Group B spans from 60 up to 90, so we expect much higher variability. This example is designed to show how the 5-number summary and box plot capture those differences quickly. In practice, these could represent two different sections of a course, or perhaps results under two different testing conditions. Our goal is to summarize each group and then compare them using the tools we've discussed. Let's summarize the key features of the 5-number summaries for these two groups. For Group A, the minimum is 70 and the maximum is 78. The median is 74, which is a very typical value right in the middle of that small range. For Group B, the minimum is 60 and the maximum is 90, and the median is 75. Notice something interesting already. The medians are very close: 74 for Group A and 75 for Group B. So in terms of center, these groups are similar. But in terms of spread, they're very different. Group B has a much wider overall range, and we would expect its quartiles to be farther apart as well, meaning a larger IQR. This is exactly the type of situation where comparing means alone could be misleading. You might conclude the groups are basically the same because the medians or even the means are similar, but the variability tells a very different story about consistency. The 5-number summary keeps both center and spread in view at the same time. Finally, let's interpret what the box plots would show for these two groups. Group A has a relatively narrow box and short whiskers because its values are tightly clustered between 70 and 78. That indicates low variability. Most students in Group A scored in a similar range. Group B has a wider box and longer whiskers because its values extend from 60 to 90. That indicates much greater variability. Scores in Group B are more spread out, meaning performance was less consistent across students. Yet, despite that difference in variability, the centers are similar. Group B's median is 75 and Group A's median is 74. So a side-by-side box plot comparison communicates a key insight very quickly. Similar typical performance, but very different consistency. That's one of the major reasons box plots are so valuable. They help us see not only where the data are centered, but also how spread out they are, whether there may be skewness, and whether extreme values exist that deserve attention.